All right, today's another crazy lecture. It's called Connectivity and Electricity. So let's see what we've been up to recently. Uh, so we've been doing a couple lectures in a row about random walks. One was about the existence of a stationary distribution. And then last time was this kind of Gaussian random walk to solve this discrepancy problem. Okay. So before I explain, I wanted to first ask some questions. Okay, so connectivity, right? You guys all know this problem. You're given some undirected graph. Today, everything's going to be an undirected graph. And you just want to know for S and T if there's a path from S to T, right? You guys have all uh, done this before. And what kind of algorithms do we use to solve this problem? Yeah, BFS or DFS. And they basically all have this common feature of, marking all of the places you visited, right? So you just say, oh, I've already been here, I've already been there, I've already been there. And you mark the vertices, and that makes sure you don't revisit the same vertex, so you don't get stuck in infinite loops and stuff like that. And eventually you'll search the whole graph, right? Okay. But, uh, a really important feature of both these algorithms is these breadcrumbs, these markings, okay? So the conceptual question we're going to ask today is, can you roughly do anything without breadcrumbs? Okay. All right, let me actually unveil these questions slowly. Okay, so in other words, we're going to be focusing on space. So, okay, so I know that we can use linear space and linear time and solve connectivity, right? This breadth first search, depth first search. All right, and otherwise I set up some fun questions for us. So as usual, so I'm going to ask you whether you guys think we can do it in polylogarithmic space or really anything sublinear. It's fine. So first of all, who's not going to vote? Okay. All right, who thinks that we can do it in polylogarithmic space? Oh, most of the class. Yeah, I would say like 90%. And who doesn't think it's possible to do it in less than linear space? Okay, one. Okay, as usual, liars. Okay, all right. Okay, so the answer is yes. What's the answer? Some of you guys may know this. Anyone taking complexity right now? I know some of you are. You might have done this in complexity. It's a divide and conquer algorithm. It's not polynomial time, actually. Well, it's called Savage's theorem. Do you guys do Savage's theorem? You roughly guess the middle point and see if you can get there and stuff like that. So that takes quasi-polynomial time, but it only uses polylogarithmic space because actually you only go through one part of the recursion tree. Okay, fine. And that's deterministic. All right, let's make it harder. Okay, how about just log n space? So Savage's theorem, if you had known it, actually uses log square n space, roughly because there's a log n recursion depth, and each step you need to write down the name of one vertex. So, okay, one sec. Why is log n space first like a lower bound? So why, okay, I'm going to ask if we can do log n space, but let me first ask why we probably can't do better than log n space. Yeah. Yeah, so log n is just a space to write down the index of a vertex, one out of n. Okay, so just to remember a vertex is going to take you log n space, so we're probably not going to do better than that. But can we roughly get then log n space? That's as good as we could possibly hope to get. That's the question. All right, who's not voting? Two. Okay. Who just lied about not voting? Okay, because we're going to make a category of double liars. Okay. Who thinks we could do it in log n space? Okay. Seemed like a lot. Who doesn't? Four. Okay, this is probably more like 90%. Okay, good. I think you all voted one of the things. Okay, so the answer is actually yes, and that's going to be the topic of this lecture. Okay, and we're going to do a very simple randomized algorithm. Okay, all right, so okay, so you can do it randomly. One last question. Is there any hope to do this deterministically? Okay, all right, so who's not voting? Who just lied about not voting? Who thinks yes? Okay, now it's down to like 50%. Who thinks no? About 50%. Okay. So the answer to this question is also yes, and this will be maybe like 2 weeks from now. Okay. And that's only a result that's less than 20 years old. So that's a pretty major breakthrough. Okay. All right. So these are the topics of our lecture. So we're going to talk about how to do connectivity in log n space with a randomized algorithm, and we're going to be talking about some concept related to random walks, something called hitting time, and something called cover time. And then this is one of my favorite lectures because it makes such a funny or kind of unexpected connection to electrical networks, which I'll describe, and have become a more and more important topic within graph algorithms for the past 20 years. Okay, so it's going to be really cool, from at least it's cool to me. All right, so anyone want to try to guess an algorithm? So you're trying to figure out if you can get from S to T, and you can roughly only remember the name of a few vertices or maybe a counter. So this is like log n additional space. Like you can look at the input, but you just can only use log n additional space. Yeah. Okay. Can you do some kind of random walk except maybe you start at S and you try to like diffuse or something? But of course, the tricky part is that you can't really keep track of many vertices values at once. Track of a constant. That's going to be tough. But there's other suggestions? Oh. Yeah, you just have to answer yes. You can't report. You don't have to report the path. The path is going to be too long anyway. I gave you S and T, and I just say, can S reach T? You're given the entire graph, but otherwise you only have log n extra space. Yeah. Yeah, that's exactly right. So that's even simpler than your suggestion. All right, so here's the algorithm then. You're going to repeat log n times, not a big deal. We'll just start at S. We'll randomly walk for some polynomial number of steps. If you reach T at any point, you just say, okay, I found it. Okay. And if you don't, you try again. You try log n times. So we'll show that the inner part, if S and T are connected, will succeed with constant probability. So the odds of failing log n times or so, is very low. Okay, so you'll get a high probability success if they were connected. Very simple algorithm, obviously. It's almost the only thing you can do in log n space, which makes you wonder how the hell we're going to do it deterministically in log n space. Okay, yeah, so why does it take log n space? So a random walk, I really just need to know where I am, right? Because especially, great thing about random walks, it doesn't care where you were previously. Just where am I now, and I pick a random neighbor. So I need log n space to maybe write down, say, S to start. I'm starting at S, and in each iteration, I pick one of the neighbors, which is up to n neighbors, right? So I generate a random number between 1 and n that takes log n bits. Uh, yeah. Uh, well, we're going to directly show that mn steps is enough to guarantee it succeeds with constant probability. So the log n just ramps it up to high probability. M is the number of edges, n is the number of vertices. M and n sound and look the exact same as usual. Yeah.
The number of times we repeat does not affect the memory, right? Because we'll just reuse.
Yeah, but also you can count to log n using log n bits. One thing worth pointing out is that you do need to keep track of how many steps you've taken, so you know when it's a good time to give up, but you only need log of mn bits, which is log n. So you have room for a counter as well. So you need a counter and keep track of which vertex you're on. Okay. All right, it's a very simple algorithm. And really, this is just a question about understanding some properties of random walks on undirected graphs. So the two kind of vocab terms I'm introducing, one is called the hitting time. So the hitting time from S to T is, oh, you start at T, start walking around. How long does it take to get to T? Okay. The other is what's called the cover time. Oh, I start at S, and how long does it take to visit everyone, cover the entire graph? Okay. And what we're really going to do is just going to prove some theorem about the cover time, and then that'll suffice. So the theorem is, if G is connected, then the cover time is at most m times n minus 1. I might be missing a factor of 2, but it's okay. Okay. So in roughly mn steps, you actually not only expect to visit T, you expect to visit everyone. Okay. So by Markov's inequality, you will probably visit in 4mn or something, right? And then beyond that, you can ramp it up with the log n repetitions. So really our class is about proving this very basic theorem about upper bound on the cover time of graphs. Okay. No matter the graph, so even if the graph looked like a long path, maybe that might seem bad. Another graph that might seem bad is something where you have like a very large click here and then like a path that sort of like leaks out. Because it's sort of hard to get out of the large click because most of the time the random walk is going to be bouncing around in here. It's going to have a tough time escaping, stuff like that. Right? But we're saying no matter the graph, an upper bound is m times n minus 1. Yeah. When is it tight? Well, that sounds like a good homework problem. I know that I should know this at the top of my head, but I haven't, so we can look it up. Yeah. Yeah, it's expected time. So with respect to our algorithm, I'll just apply Markov's inequality and say, oh, what are the odds of being more than 4 times the expectation? Oh, that's 1 in 4. So algorithmically that suffices. Yeah. Yeah, sure. Sure. Yeah, it's still slower than BFS or DFS, partly because BFS and DFS is so efficient, right? Because it never revisits another vertex. Random walks may revisit the same vertex over and over again. Yeah, that's a trade-off between space and time. I guess the product of space and time is roughly the same between the two. Or maybe one is m squared and this one is mn. So maybe this is better. I don't know. Okay. All right. Questions. Okay, for specific classes of graph and stuff like that. So yeah, this is a worst case bound. We are going to study. So okay, the question is, do people study specific graphs or get better bounds and stuff like that? And very much so. The answer is absolutely yes. But I mean, first of all, I think there are people that probably study like eccentric hypercubes or like very specific graphs. But we will also study graphs with certain parameters. So actually, we'll find connections between like Remember the sparsest cut problem we did, which is roughly, can you take a graph and find a small set of edges that roughly divides the graph in half? Okay. So imagine a graph that does look like that, like two dense parts with a few edges connected in between. A random walk is going to have a tough time going across the sparse cut. It's always going to tend towards the dense parts and have a trouble getting across the bridge if it's a completely random walk. So graphs with very sparse cuts are going to have worse kind of cover times and stuff like that. And if you can guarantee there's no sparse cut, roughly the whole graph is really well connected, then you will visit the graph faster than the worst case bound and stuff like that. That has interesting connections to the eigenvalues of the random walk and stuff. So you guys have that to look forward to. Okay. But at some level, we will take some kind of parameterized approach. And this will all actually factor into how to do things deterministically as well. Yeah. So we're only at the tip of the iceberg. These are good questions. Okay. All right. So this is where we're going to do something different and talk a little bit about electrical networks. Okay. So, I'm just going to pose things in pure kind of CSE graph terms. Don't ask me too much about the physics. Okay. Okay, so electrical network. For us, it's just an undirected graph. For today's lecture, we can just assume it's unweighted, but in general, electrical networks may have weights called resistances. I'll introduce them in a moment. Okay, okay, so here's like a battery, and it's sort of pushing one unit of electric flow from T to S, and that electric flow needs to kind of go back across from S to T to sort of complete the battery or whatever, right? So this is, how does electricity actually would navigate something like this? Okay, so you might have heard the phrase, so you need to roughly send one unit of flow from S to T, right? And the question is how? Now you might have heard the phrase, the path of least resistance. Okay, electricity and various other things in physics will take the path of least resistance. Okay, so how might you interpret that phrase, the path of least resistance, from S to T? Shortest path. This is the most natural answer. So what is the shortest path in this graph from S to T? Along the top is 1. So, okay, so that looks like 5. Oh, there's a, okay, I see it. Okay, so here's the path of length 3, right? And so then, yeah, the battery sucks in 1 unit, pushes out 1 unit, and electricity takes the path of least resistance. So as computer scientists, as humans who like to add up numbers, this is easily the most logical thing, right? But I guess that, well, I would say that physics is not a person who does combinatorial optimization. Physics likes to do calculus. So physics is going to interpret least resistance as a sum of squares. Okay, so let me explain. It's not actually going to be the shortest path. So the more general setting was weights. Each edge is given some resistance, R sub E. So for us, all the resistances are just 1 uniform, so not a big deal. This is only for the future lectures. Now, for any kind of flow, which I think of as assigning values to edges, okay, the sort of electrical energy of that flow will be summing up over all the edges, the resistance, which might just be 1, times the flow on that edge squared. Okay? The flow on that edge squared. We were thinking of just sum of flows, right? So then I just want 3 edge path because then that seems like the minimum. But here we're actually minimizing the sum of squares, Fe squared. Okay. From one perspective, that might be unusual, but from another perspective, actually, there's lots of people who prefer sum of squared types of formulations to sums, different fields, right? Okay. So the electrical flow is going to be the flow of least electrical energy by this definition. Okay. So what does that imply? So for something like this is not the actual electrical flow, I just drew something. But in general, it's going to want to spread out the flow around many edges, right? Because if I send, 0.2 units of flow along this edge, the energy is 0.2 squared. So those small numbers get squared and really go down. Okay, so electricity is going to kind of naturally spread out over the edges. This is not the actual optimum solution, but it is technically a flow and it is mildly diffuse. So that's how electrical networks work. Okay, so they're going to be minimizing this convex sum of square function rather than the kind of the more discrete function that we typically have in mind. All right, so okay, so that's what electrical networks are. Now, okay, so I'm gonna kind of give you all the background on electrical networks, but I'm going to try to present it from a relatively unified point of view. I really want to say this is just a simple convex minimization problem, relatively simple. Maybe some notation will be kind of new, but modulo some new vocab, relatively simple. Okay, and just by kind of studying things like first order conditions from a convex optimization point of view, out will come up with those famous things like all these physics laws and stuff that you've heard of before. Okay, so let me just set up the mathematical notation first. Okay, so the first thing is I want to so it's an undirected graph, but I want to just represent flows by a vector indexed by edges, right? Some vector f indexed by edges. So I have to decide like, oh, what does a positive and negative value mean when there's no particular direction originally, right? So we're going to just orient the edges arbitrarily. Doesn't matter what orientation you pick, just consistent henceforth. So that when I say that f of e is bigger than 0, I mean that, oh, I'm sending f of e units in the direction of the orientation. And when it's less than 0, I'm sending that absolute number of units against the orientation. Okay, so I'm just fixing orientation so I understand what plus and minus mean. No big deal. Okay. All right. Now, okay, so flow constraints aren't super complicated, right? What goes in has to be equal to what goes out. And all I'm pointing out here is that that's a linear function. Okay. So define this function b that takes as input a flow vector, f, and outputs one coordinate for every vertex. Bf of v will just be the net flow at v, the amount of flow going in minus the amount of flow going out. Okay? And all you need to know about this is that it's a linear function. If I added up two flows on top of each other, then the net flow will be the sum of the original net flows, right? So as soon as it's a linear function, you know that, oh, okay, that means there's some underlying matrix. Okay? But for me, I just remember what it means. And I don't worry too much about the coefficients. Okay? So I guess that would be some examples, some flows going in, some flows going out. The net flow is 0, so Bf of v is 0. Really, the main high level point is that net flow is a linear function of the flow. Okay? All right, so I think there's something here. All right, and so I kind of want to take my flow constraints. Like originally I'm saying I want an ST unit flow. I want to send one unit of flow from S to T. And all I'm trying to say is, hey, that's a linear system. Okay? So in particular, it's solving BF is equal to D, where D is defined by, all right, so what would D sub V be if V is equal to S? 1, right? Because I want the net flow at S to be 1, net flow out of, I guess it's net flow out. Okay? And then T, -1, and then everywhere else, 0. Okay, so that means I'm conserving flow. No big deal, but it is an important point that it's a linear system of equations because that has some mathematical structure that we can use. Okay. All right, so again, so electrical flow is just this convex minimization. I'm just minimizing the sum of squares, the electrical energy, subject to a system of linear equations. Okay, at the end of the day. The electrical flow is just in this context for optimum solution. Okay. So, okay, so here, instead of just kind of thinking in terms of electricity and electrical flow and stuff like that, we're going to take a step back and say, okay, this is some relatively simple convex minimization problem. And that alone should already give us some structure. Okay, so what we're going to do is maybe study some general optimality conditions for systems that look like this, minimizing something subject to linear equations, and then we'll figure out what it means for electrical networks. Okay. All right, so here's maybe the most abstract part of the class, the one time we were not really talking about anything specifically, but just going through a quick math. All right, so let's consider any problem of the form, minimizing f of x subject to ax equal to b. That's fairly general. Okay. The claim is that if x star is the optimum solution, then the gradient at the optimum solution is equal to A transpose Y for some Y. Okay. So actually, let me take one step back. You guys have probably seen, suppose, for example, we ignored the constraints. Okay. So imagine, you guys may know this. So let's say I'm solving just some problem of the form minimizing f of x, where f is convex, right? Then what do I know about the gradient at the optimum solution? Let's say f is strictly convex, so it's really curved. It's equal to 0. Okay, so when you're doing global minimization, the gradient needs to be 0, because if it was not 0, then there's some direction in which you can improve your solution. Okay, so that you guys know like the back of your hand. So all this is doing is sort of saying, okay, I'm working in some subspace of x's where ax has to be equal to b, and otherwise minimizing that. So if the gradient isn't 0, but somehow it's going in a direction that would break your constraints, some of these arguments don't immediately extend. Okay, so that's really the technical adjustment we need to make. But it's sort of strong because it's saying at some level, this A transpose Y sort of gives you a certificate for the optimum solution. Okay, but so let's just do this. This will be probably the most trying part of class, like patient trying class, and then we'll go back to more combinatorial things that'll be more fun. So bear with me. Okay. So, this is roughly going to follow from some basic linear algebra facts. So let me just present them. I won't prove anything. And you guys have probably seen some of this before, in which case it's just a refresher. So if you have a linear map A going from some vector space X to some vector space Y, there's some terminology. So the vectors that map to 0 is sometimes called the kernel, sometimes it's also called the null space of A. Okay, it's a vector space because if X and Y both map to 0, then X plus Y will also map to 0 because A is a linear function. Okay. The image of A, as you guys know, is just all the things that can be output. The co-image is maybe less common, but it's going to be the subspace orthogonal to the kernel. Okay, so this is the vector that's of x's, where for anything z where az is equal to 0, x dot product z is 0. Okay, so there's some space that's all getting sent to 0, and then there's this other space that roughly never gets sent to 0, and they're orthogonal to each other. Okay, so one way to interpret what the kernel and the co-image is doing, so you roughly take the entire input space X and you split it into two orthogonal subspaces. One is the kernel and one is this co-image. Okay, the kernel, it's all getting mapped to the 0. Okay, meanwhile, if you just restrict A to the co-image, then you're actually going to get a bijection with the image. Okay, so at some level, we're saying if you kind of ignore the kernel in the linear algebra sense of the kernel, which means in the linear algebra sense of ignore, which means you work in the orthogonal subspace, then what you're left with is a bijection. If you get rid of all the things that map to 0 except for 0 itself, then what's left is a bijection. Okay. All right, so that's one thing. And the other fact has to do with just the transpose. Okay. So A transpose is going in the other direction. Okay. the image of A transpose is actually always equal to the co-image of A. And the co-image of A transpose is equal to the image of A. So A and A transpose are not inverse to each other. A times A transpose is not equal to identity, but they are both giving bijections between the same set of vectors on one side orthogonal to the kernel. Okay, that's the main facts. Okay. Not sure if you guys have seen this or not. It might show up in like the first half of a graduate linear algebra class. Okay, but let's just, it's on the right hand side if not. Okay, so now let's look at this problem again. Okay, so all right, so okay, so let's look at f prime of x star. Okay, okay, so if we look at our intuition from the unconstrained setting, we know the gradient has to be 0 because otherwise you'll be able to move against the gradient and decrease your value, right? Now, that's not exactly the case because there's these constraints A we have to respect. But I'm going to claim that the analogous statement is that f prime x star has to be in the co-image of A, which is to say it has to be orthogonal to the kernel of A. Okay, now that is the claim is that the gradient dot product with z has to be equal to 0 for all z where az is equal to 0. That's just expanding out the meaning of co-image. All right, but this actually makes sense. So why does this have to be true? Okay, so let's say that it wasn't true, right? Let's say that maybe you had less than 0. Okay, then you know that f of x star plus a very small amount of z for sufficiently small delta, okay, is roughly f prime of x, f of x star plus, right? Because a gradient tells you what the direction looks like in that, what the change in f looks like in that direction. This is just a definition of the gradient, right? So if this was anything, say, less than 0, then for a really small step size, this thing will be less. And you'll be able to improve your solution. Meanwhile, because z is in the kernel, that solution would still be feasible. Okay, so the kernel represents the directions in which you can move x star, okay, without violating any constraints. Okay, so, and if it was greater than 0, then of course you would do the same thing with negative z. That will get you less than 0. Okay, all right, so if f prime of x star is in the co-image, then what do we know? Now we have to use some of those facts. That means it's in the image of A transpose. That means there's some y, so that A transpose y is equal to f prime of x star. Okay, so some linear algebra facts that may have been new, maybe not, but are relatively elementary, mixed with basically your intuition from the undirected setting, right? So basically we just needed a little bit of linear algebra to go from undirected to linear constraints, or unconstrained to linear constraints. Okay, are we okay with this lemma? Okay, good. We'll just put it in a box now. Right, where is it? Okay, so that lemma is now sitting in the bottom right. Let's go back to talking about electrical flows. Okay, so I'm going to try to just take this simple mathematical fact. I mean, I think the only thing to highlight is that all we used is that we're minimizing a convex function subject to a linear system of equations, and now out will come like a lot of interesting facts about electricity that I didn't know, right? So, okay, so here's one claim. So let's say F is routing D, right? So B times B of F is equal to D, okay? Where D is some set of demands. The claim is that F is an electrical flow if and only if F is equal to R minus 1 B transpose P for some vector P. Okay, so any optimum flow, electrical flow, has this sort of vector P sitting underneath indexed by vertices. Okay, that also certifies that it's an electrical flow, right? So that means if you had some F and you weren't sure if it was an optimum solution, but if you had a vector P that so that this will be true, that tells you that F is automatically an optimum solution. See, so this is actually giving you a certificate of optimality. Certificates are important. Okay? All right, so anyone want to guess what the approach will be? R is the resistances along the diagonal. Oh, I don't know if I ever wrote that, huh? Okay. Okay. So put all the edges along the diagonal.
So with our simple example of equal weight on the edges, R is just the identity.
Yeah, yeah. We can even ignore R for the sake of our discussion. Yeah.
We can just use the name and just write down
Yeah, okay. So what is the convex function we're trying to minimize, right? Okay, there's some mix up of notation here. So I'll write phi as the function. So phi of f, which is equal to 1/2 sum E uh, resistance times the flow squared. Okay. So if I wanted to look at the derivative, say it was a particular edge E, this is equal to RE FE. Okay. So whatever, the fancy pants way to write this is, okay, RF, where R is just putting the resistances along the diagonal. Again, sorry for not introducing that notation. Okay. And now the claim, okay, so that addresses what's the function. And now what's A, right? We need the flow to satisfy BF is equal to D. Okay, so A is equal to B. Okay, so what we showed is that if F is an electrical flow, then the gradient RF is equal to the gradient at the electrical flow, which is equal to P transpose. Instead of Y, I'll use a P. Okay, and then you can invert this diagonal matrix. Okay. All right, so that's one direction. Now suppose that F is an electrical flow. No, sorry, F is equal to this thing for a set of potentials. And now I want to argue that these potentials certify that F is optimal. Let's see what the shortest way to do this was. Okay. All right, so okay, so what we're going to do is we're going to prove this by comparing it to any other flow F, G, okay? So let's let G be another flow. So G also routes d. Okay, and we know that for a convex function phi, right? We always have phi y for any convex function phi. We always have this thing, right? Where if I am looking at a point on the curve and I draw out what the derivative would project, the curve is lying above the derivative. Okay. Okay. So if I apply that here, maybe it's more convenient for us to write it this way. Okay. So I'm going to take y to be g, x to be f, and phi to be the resistance stuff, the electrical energy. Okay. So, okay. So one thing I want to just quickly mention is that uh, this term, okay, a slightly more compact way that I'm going to use to write this is to write it like this, but it's the same thing. Okay. All right. So if I look at one electrical energy minus the other electrical energy, okay, I know it's at least, okay, so what's the derivative for F is going to be RF, which we already did, times G minus F. Okay. Still with me? Maybe. Okay. But now I'm going to plug in this fact. Okay. So we get R minus 1, B, P, G minus F for some P. Okay. Of course, this cancels out. And we flip the B to the other side. Oh, sorry, this is a B transpose, isn't it? B, G minus F. Okay, so we get something like this. Okay. I'm going to claim that last term is 0, but my question to you is why? The last term is 0, but why? I'm saying this is 0. Then we'll be done. Because then, sorry? Not necessarily constant for all x, but okay, so B is the net flow of G minus the net flow of F, right? BG minus BF. And then we assume that G is also routing the same demands as F. Yeah. Okay. D minus D, that gets us 0. Okay, so whatever. The electrical energy of G is at least the electrical energy of F or any other G that's routing the same set of demands. Okay, somehow the existence of this P will certify an electrical flow for you. Okay. All right, fine. So what is this P? This P is called the electrical potentials corresponding to this demand. Okay. And the fact that for any electrical flow, there's always electrical potentials in correspondence, like this is called Ohm's law. Okay, so it's one of those basic laws of electrical networks. But really, it's nothing more than if electrical energy is optimizing this simple function, what are the first order conditions, the optimality conditions for that problem? Okay. All right. Okay. Marching on. This particular expression up above B R inverse B transpose. It's called the Laplacian of an undirected graph. It's actually corresponding to, it's really the Laplacian of the graph where the edge weights are actually the inverse of the resistances. Okay, so this will be something we'll get used to. Okay, but let me first, to help understand the Laplacian, just look at what it does on some input vector x. Okay. All right. So if we expand this out, right? So I just put L is equal to B R minus one B transpose, and I put the B's on the opposite side, right? And we unroll a little bit more. Okay. So we're summing over E, 1 over the resistance of E, B transpose X, E. Okay. We didn't look at B too carefully before. This should be squared, shouldn't it? So we didn't look at B transpose too carefully before, but if you did think about it, so what's it doing? So that doesn't matter. Okay. So for each edge E, what B transpose X is going to do is it's going to give you XU minus XV, where UV is that edge. Okay. So B transpose XC squared is giving you XU minus XV squared. Okay. So this is measuring some kind of potential. Okay. So what's it kind of doing? You're taking as input some kind of vector of like potentials over vertices. Okay. And what the Laplacian does is it sums over all the edges, and it says, okay, here's an edge between U and V. What are the values at the endpoints? And then let me look at the difference and square it. Okay. So that means minimizing the Laplacian over X is trying to get values that are closer for edges, especially with small resistance. Okay. But let me give you an example that's a little more combinatorial, so it's easier to see what's happening. Okay. So what we're going to do is study cuts, right? So let's look at a set of vertices S that's splitting the graph in half, right? So here's S, here's not S, and then you have all these edges in between, right, of various weights. Okay. So let's plug in this indicator variable that's assigning 1/2 to every value that's in S and minus 1/2 to every value that's not in S. Okay, so this will get like 1/2, that'll get minus 1/2. Okay. All right, so if I expand out XLX by our formula, okay, any edge that's on where if both endpoints of the edge are on the S side, you'll get 1/2 minus 1/2, so that's just 0, right? Because you're taking the difference of endpoints squared. And if they're both on the bar S, the complement, you'll get negative 1/2 minus negative 1/2, and you'll get 0 again. So really all that's interesting is the edges that are going across the cut, 1/2 minus negative 1/2, that's 1. Okay, I only chose 1/2 so that it comes out to be 1. Consequently, okay, so then basically you get 1 point for every edge in a cut, 0 points for everything else because the endpoints are the same. Okay. And that's the weight of the cut if the weights were the inverse of the resistances. Okay. All right, so two things. One, that's one way to help understand what L is doing a little bit because we understand cuts combinatorially. So L actually has enough information to give you the values of all cuts in the graph. But taking a slight step back, one thing that's kind of remarkable is that the definition of L is some combination of stuff that came up in our study of electrical networks. B R minus one B transpose. And we've somehow connected that back to something we understand really well, which is the weight of cuts. Okay, so we'll expand on that further in upcoming lectures, but I wanted to point that out now. Okay. Did I point this out before? Did I mention effective resistance? Okay, one sec. Did I forget something? Okay. Oh, okay. So here it was. Sorry. Okay. So if we look at our optimization problem, okay, at some level the graph is fixed, right? So B is fixed and R is fixed. Okay. And F is actually not input, right? Because the algorithm chooses F. The only remaining input is D. So if you choose D, out comes some perfect choice of F for it. Okay, and along with some corresponding electrical energy. So the value of the optimization for a particular value of D is sometimes called the effective resistance of D. At some level, it's because the network is sort of acting like one edge of that resistance between those endpoints. If D was an ST pair. Okay, so parsing this lemma then is saying that the electrical flow, the optimum solution for a particular value of D is equal to, again, some very nice closed form looking thing for L. Okay. Let's see if this is, okay, so this is not so hard to prove. We just straightforward, so let's do it. Okay. So we're getting a closed form solution for D. So, but yeah, maybe I should point this out. So the left-hand side is encoding some kind of minimization problem, right? So this is equal to min FRF, maybe 1/2, subject to BF equal D. Okay, so that was what we've been working with so far. But in particular, it feels complicated in the sense that I'm minimizing something subject to linear constraints, right? It feels like there's at least two kind of moving pieces there. The right-hand side is not an optimization problem. The right-hand side is just take L inverse and apply D to it, and you just get the value you're looking for. The left-hand side looks like an algorithm problem or something, right? It looks like an optimization problem. I give you D, now go find F, minimize something, optimize something. The right-hand side is saying, take D and just multiply matrix. Okay. Okay, so how do we prove this? So let's let F be the electrical flow. Let's let P be the corresponding potentials for this optimization problem for D. Okay, so F and P solve the problem. Well, we know F solves the problem, and then when there exists some P, so that F is equal to R minus 1 B transpose P or something, right? Okay. All right, so I think this, from what I can tell, we just start plugging things in. So we start with this. This is the effective resistance of D. Okay. And we start plugging in this thing for P. So this P makes like life very easy. Okay. So I've just plugged things in. It looks a little ugly. Okay. And then some terms cancel out. P, B, R minus 1, B transpose P. So it looks like what we did was we canceled out one pair of R's, and then we threw one R minus 1 to the other side, and then the B transpose flipped over to a B. Okay. And this, okay, if we look at what L was, okay, so what did I write? Okay, so now if you look at something like, okay, that's okay. Okay, so all right, so we get something like BLP. Okay, and what we're going to do is we're going to put in one L and one L inverse. Okay, it's really the pseudo inverse because it's not full dimensional, but that's okay. All right. All right, and now, lastly, if we look at LP and expand things out, okay, something like this, then out comes BF, and out comes D. Okay, so somehow there's all these equalities going on because BF is equal to D and F is equal to B, R minus 1 B transpose P, right? You have all these equalities, and somehow it's like a knife cutting through butter. Okay, and we can plug this in, and we get this closed form thing. Okay, so this is also some very nice identity. Okay, so electrical networks have lots of structure. I guess that's all I want to say. It's all sitting on the right-hand side for us to now finally go back to random walks and figure this thing out in the last 15 minutes of class. Okay, but we'll keep reusing that electrical network stuff in upcoming weeks because it's very closely related to studying undirected random walks and undirected graphs. Okay. All right. So my goal now is to try to prove that theorem that the cover time is at most m times n. Okay, and then somewhere along the way, these electrical networks and all these fun facts are going to come into play. Okay. All right, so let's fix some T and V. And what I kind of want to study is what is the hitting time from U to T for various values of U. Okay. So the first one actually is not as hard. What's HT of T? So this is a good warm up. 0. I hope it's 0 and not 1. Okay. It's definitely 0. All right. Now HT of T doesn't have a closed, it's not just a number, right? It could depend on things. But we could sort of like model it recursively, right? So, okay, so if I'm trying to go from U to T, but U is not equal to T, I'm going to take one step, one random step, okay? And then I'm going to choose a random neighbor. So, okay, there's degree U neighbors. I'll choose one of them with equal probability. And so we'll sum over all the neighbors of U. And so once I go to V, then what's the time to get to T in expectation? Huh? Oh, that's true. Oh, okay, but maybe more simply, what you're describing is HVT. Okay. So I really meant to say is that, okay, these H's satisfy some kind of linear equation, system of equations. Okay. All right. So simple enough. Here's where things get kind of surprising, in my opinion. I think things get surprising. Okay. All right. So we're gonna take these hitting times to T and use that to define a set of vertex potentials. Somehow we're going to think of that in terms of electrical networks. Okay, so P of U is the hitting time from U to T for all U. Okay, and then we're going to let F be the corresponding flow. Okay, so F is equal to B transpose P. There's no R for us because the R is all ones now. Okay. All right. Okay, so what we wrote this down, right? Okay, so just plugging in, I'll get PU is equal to 1 plus 1 over degree U, summing over all the neighbors, PV, right? Okay. And if I might multiply both things by the degree, we get degree u pu is equal to degree u plus the sum over all the neighbors. I'll just write tilde as a shorthand for neighbors of u, okay, of those potentials. Okay. And now what I'm going to do is I'm going to take that sum and throw it over to the other side. So we get the sum over all v that's a neighbor of u, p u minus p v is equal to degree of u. Okay. I should add that this is only when u is not equal to t. Otherwise it would be. Okay. All right. So now what? Well, this equation, f is equal to b transpose p. Okay. If I look at one of these edges, this is equal to pv minus pu if the edge u was directed from u to v. Okay. So this is actually equal to the sum over all neighbors of u, sort of the flow from v to u, okay, which may be positive or negative. So let's imagine orientation is set up so that all the edges are pointed out of u. And it just flips some signs and doesn't change anything. Okay. All right, so in other words, is equal to degree u. So this is the net flow summing up over all these edges. Okay. Okay, so we are saying that this is the net flow into u is equal to the degree of u. Okay. So somehow what we've done is we had these inspired vertex potentials. We plugged it into this simple recursive formula that the hitting times were satisfying. And suddenly we're able to figure out what were the demands for all the vertices except for t in some corresponding flow. Okay. So if all the vertices are outputting degree of u, right, then that means that they're all sources, right? They're all pushing out flow. So t is the only sink because t is the only vertex not covered. And so the net flow into t is so sum over all vertices except for t, the degree of u, which is 2m minus the degree of t, because it's only those edges that aren't getting counted twice. Okay. So t is encoding some crazy flow, right? That's outputting flow equal to sending flow, or every vertex is a source equal to its degree, and then v, this is not drawn correctly, is outputting flow proportional to its degree. So instead of negative 99, it should have been something else. Okay. Oh no, it should have been 2m minus its degree or something, right? Maybe it is 99, I don't know. All right, so, okay. So P is encoding some flow, routing this. Okay, good, making progress. Yeah, perfect, thank you. Okay, all right, okay. So somehow we're going to use that. for this lemma. Okay, here's where things start to get more practical. I'm looking at some edge UV, and I'm saying what's the hitting time from U to V plus the hitting time from V to U, and it's claiming that is 2 times the energy of a unit UV electric flow. Right? These are like crazy statements. The left-hand side is talking about hitting times between two vertices, two endpoints of an edge. The right-hand side is talking about electrical flow, right? If I had presented as the first slide of this lecture, you'd have been like, what the hell? You know, that's impossible, right? They have nothing to do with each other. Okay, so let's see how to prove this. Okay. All right, so let P be the corresponding potentials for V, the hitting times to V. Let Q be the hitting times to U. And let R be the difference. Okay. All right, so we have, okay, so this is what? This is equal to PU plus QV. Okay. This is equal to PU. Since these are equal to 0, I can subtract them. I guess I can. Something like that. Those were equal to 0 because the hitting time from V to V is 0. Hitting time from U to U is 0. Okay. And so this is, I got something backwards, didn't I? Okay, this should be QV minus QU. Okay. When we put this together, we get RU minus RV. Okay. All right, so let's look at the demands D, where dV is equal to 1. I'll write x, sorry. dx is equal to 1 if x is equal to u, negative 1 if x is equal to v, and 0 otherwise. Okay. All right, so RU minus RV can be written as D dot product R. Okay. All right, so let's see. One second, I'm just working off some notes here. Okay, so we have R is equal to P minus Q. We have B transpose R is equal to B transpose P minus B transpose Q. All of these are describing flows. Okay. Now, okay, so B transpose P was floating degree units of flow out of all the vertices except for U. And then B transpose Q is routing, the degrees out of all the vertices except for V. Okay? So except for U and V, everything will cancel out because one subtracts the other. For U, it's taking in 2m minus the degree, and then there's another degree term coming here. And for V, it's taking in 2m minus degree, and it's getting another degree term here. Okay? So that means that what this thing routes, so this routes 2m units of flow from U to V. Should be an S. Okay? So the flow corresponding to R, which is the difference of two potentials, giving you another potential, is routing 2m units of flow from U to V. Okay? All right, so B transpose R is equal to 2md. I think we're actually gonna finish, be able to make it, because the last lemma is going to go rather fast. Okay, so just finishing this part off though. Um, okay, so that means that 1 over 2 mr, okay, so this also means that 1 over 2m B transpose R, or maybe R over 2m is equal to D, right? So that means that 1 over 2m times R is the electrical potentials for routing 1 unit of flow from U to V, which was what we decided was D. Okay, so let me put everything together. Okay, so HUV plus HVU, which was equal to uh, whatever, PU minus QV, which we already showed was equal to this RD. Let me write it this way. DR. Okay. This is 1 over 2m B transpose R, which is 1 over 2m B transpose R, B transpose R, okay, which is 2m times, if I put over 2m down here, okay. This all seems crazy, but let me interpret. This is the flow routing 1 unit, this is electrical flow routing 1 unit of flow from U to V, because R over 2m was the corresponding electrical potentials, okay. So flow times flow, and that will give you the electrical energy to route 1 unit of flow from U to V. Whatever. Energy for 1 unit from U to V. Okay, that was the lemma. Okay, we're so close. All right. Here is the last thing we wanted to prove. I know we're a little over. Okay, finally, we want to show the cover time is at most 2 mn. It used to be mn, but now it's 2 mn. So I guess I was off by a factor of 2. Okay, we're going to somehow use this lemma that we just proved, which was somehow the hitting times is related to the electrical flow between those endpoints. Okay? All right. Anyone want to take a stab? You have about 15 seconds. This will be the funnest part of the proof, I promise. And not just because it ends the class. Yeah.
The above equation, if we fix U to be S, and we just sweep over all the other vertices, that will be a constant.
So we're going to do something like that. So let me actually see. That's not so far from the actual idea. So let's fix a spanning tree of the graph. Take a spanning tree of the graph, okay? And fix a traversal of the spanning tree. And we're just going to say, suppose I randomly walked around and I had to go from one vertex to the next, to the next, to the next. I walk and it takes a while to get to the next vertex. And it takes a while to get to the next vertex. It takes a while and I go back up the tree and back down the tree and back up. How long would it take a random walk to traverse this tree? Okay. So in particular, if this was a vertex U and this was a vertex V, so I need to go down this edge from U to V, right? What's the expected time to do this leg of the traversal? Hitting time of UV. And then later on in traversal, you go down the tree, you go back up, right? So later I'm going to have to go from V to U. And what's the hitting time of that? Or what's the time of that would be the hitting time from V to U. Okay, and we know what HUV plus HVU is equal to. Okay, so, so the total time for random walk to traverse this entire tree is the sum of HUV plus HVU for all pairs UV that appears an edge in the tree. Okay, and what we just proved is that this is the sum of sort of unit electrical flows between every edge of the tree. Okay. All right. Now all that's left is to bound this last term. We're so close and past the time, I know. All right. So I left it as a box for you guys. You guys can get this, then you can leave. Okay. So all I want to do is analyze. I wanted a nice clean upper bound for the energy of a unit UV electrical flow for an edge UV. Oh, okay, one. Why? Oh, because I drew it there. Okay, it wasn't supposed to be drawn. Okay, so because UV is an edge in a graph, one example of a flow is sending one unit just directly from U to V, and the energy will be one. You could maybe do better by spreading out throughout the graph, but we just want an upper bound. Okay, so okay, so that's at most one. We add everything up together. Each of these is one. How many edges are in a tree? N minus one, and we get 2m n minus one. Okay, so something bizarre has happened. We spent a long time doing calculus and understanding everything more than you probably wanted to know about electrical networks. And somehow we were able to use that to analyze random walks because there's some sort of, they're both solving a very similar set of linear equations implicitly. And that's how that connection appeared. Okay. All right. Now we're actually done. Thank you.